put a couple announcements on Canvas. One is about a CARES grant opportunity. So there's a link in there if you want to see if you are eligible. I believe the deadline to apply is April 20th. So it's coming up soon. The other announcement was that Chase set up a Discord server for you all to hop on, and it gives you guys a forum to discuss, problems, things that aren't quite, setting in. And so the link is on the homepage, and I've been informed that this link changes after a while. So we'll update that if we need to. But this is the link here. You click on that, and then I know that students of mine in the past have used Discord. I have not, been involved with it, so I'm not quite sure the inner workings, but I do know that it's a widely used platform for you guys to discuss things and talk outside of the lab and lecture hours when we have Zoom. So I strongly encourage you guys to check that out. We haven't had any homework assignments yet, but as you know, the ICA is the last couple of problems are pretty technical, and as homework comes, you might want to meet up this way to help to work on that. The other announcement is that I have been approved for 2 office hours per week this quarter. So I'm looking for feedback from you guys on what days and times work well for you. I can't guarantee, you guys probably all have different days and times that are convenient, but if I can get some kind of consensus on what works best, I'll choose that. It can be 2 consecutive hours. We can split those 2 hours up for different times or different days. So if you want to have any kind of buy-in toward when these office hours are going to be set, please send me a message and let me know what works for you. Okay. What else? If you have found a partner in a topic, or if you've found another topic that you find interesting, please feel free to add it to that Miro board that we used during Tuesday's lab. Update it. It's a working document. So you can go in there, you can add you and your partner's name, you can add topics to that other side. Try to get familiar with Miro, because we'll be using it later on for you and your partner to start brainstorming for the actual outline of your research proposal. Okay. So I encourage you guys to use it sooner than later. Okay. What else? My notes here. Next week is going to be asynchronous. So that means I'm going to have a pre-recorded lecture for you to watch. It's a 2-hour lecture, like typical, but I'm going to just have that one video for both lectures. That way you don't have to sit and watch 2 full hours at once. That's good if it's a really entertaining movie, but sitting and watching a video of chemistry for 2 hours really only appeals to a small cross-section of Homo sapiens. So I'll post that video, and you can just watch it really whenever. It doesn't have to be during the regular lecture time, okay, if there's a time that works better for you. So there'll be one 2-hour lecture of material that you should watch at some point. There will be an ICA, just a couple problems that you can do at any point. And then there'll be a video for lab. It's a talk by Jennifer Doudna, who recently got the Nobel Prize in Chemistry for her work adapting CRISPR into a genome editing tool. And it's a talk she gave through UC Davis. So I want you to watch that and just do kind of a, like a write-up like we do for Journal Club. Just kind of summarize the talk and what was interesting to you about that video, just so I know that you watched it. Don't have to be anything too in-depth. Okay. Any questions, comments, or concerns? Well, then in that case, what we're going to be doing now is we're going to be moving on to the next chapter. So we finished up equilibrium in lab this morning, and now we're going to move away from equilibrium into electrochemistry. Okay. And since one of the students' feedback was that they would like to have music at the beginning of class, I've picked a song that I think is really perfect for today's lecture. So here it goes. You ready? You guys hear that? Now, if you want, feel free to stand up, stretch your legs, and we'll do some electric slides for a little bit. I don't even know if I remember, but I think you go to the left. And go to the right. Yeah, there we go. I don't have much room in here, but okay. We could do that for, that song is a good several minutes, but we got to really get into it. So hopefully that kind of get the blood flowing for a little bit or a laugh or something. Now let's dive into electrochemistry, shall we? Let me find that slide deck. Yeah.
That song is always surprisingly long whenever it's played at weddings or parties.
Yeah,
you're like in the middle of it. You're like, gosh, how much longer does this go?
It's so fun at the beginning, but then, yeah, I don't know if they loop it or what, but it's like, okay, all right. Sit down now.
So true.
Okay, here we go. Electrochemistry. So why is electrochemistry particularly important to learn? Well, I think Michael Faraday summed it up best back in the 1800s when the higher ups in Britain were saying, okay, why are you spending this time researching this esoteric thing called electricity, which really no commoner was even aware of? You know, what is the practicality of it? And Faraday's response was, one day, sir, you may tax it, right? And that definitely brought that now seemingly esoteric study, that basic research, into something that is applicable. Now, fast forward to where we are now, and electricity is absolutely vital to not only our economy, but just the way that we survive, right? So it's an example of how something starts off as being unable to apply it, but through understanding it, we find an application for it. And I'm hoping that as you think about your research proposals, you know, maybe that's an avenue you can take, right? Take something that's been discovered in a basic research level, understanding nature, and turning that into something that can be exploited and utilized to better humanity, right? Whether it's medicines or therapies or just technology. That's what it's about, right? Your research proposal should be basically saying what you want to do, how you want to do it, why you want to do it, and how you think it's going to hash out at the end, right? And so, you know, electricity, as we're going to study it in the form of electrochemistry, is going to help elucidate how things like batteries work, right? How do we get to make better batteries, which is a topic that some of the students are looking into, right? How do we get batteries that are more efficient, right? And some work has been done to do this, right? When we talk about chemical reactions, we say that most of them are going to be, in terms of electrochemistry, redox reactions. So there is a transfer of electrons in some way. And that is electricity, right? The movement, the flow of electrons. And so if you can harness the transfer of that electron from one atom or ion to another, you can get energy out of it. Okay. And as we continue the basic research to understand the nature of redox reactions, we can then get more efficient ways to generate electricity, right? So here's a couple examples of a car that is, run on a fuel cell. Okay. So essentially, fuel cells, there are different types of fuel cells, but these fuel cells that you see here are utilizing hydrogen and oxygen. And as you know, oxygen is more electronegative than hydrogen. So it's going to hog more electrons at any given moment, right? And so what they do in these fuel cells is that they separate the hydrogen and the oxygen so that when between this thin wire, so that when the electron is going to be transferred from the hydrogen to the oxygen, it hits that wire, and then now we've harnessed the electricity of that reaction. And the byproduct is water, so it's clean, right? It's not carbon dioxide and carbon monoxide. And so these are just some examples of ways that batteries are improving, okay? And really, that's the wave of the future. If you start talking to a lot of engineers or engineers that are starting their careers, a lot of them are going into battery engineering, chemical engineering, so that we can come up with more efficient batteries at not only efficient in producing energy, but in storing energy, because that's one of the biggest issues with renewable resources, is that we can generate a ton of energy from solar and a good amount from wind and water, but being able to then store it long term and deliver it in some kind of separate grid is the challenge, right? So as we get better at our understanding of batteries, we can make giant leaps to having cleaner ways of getting the energy that is so vital to our daily life and the economy. Okay. Redox reactions. Now, you guys, pretty sure you did this in Chem 101 with Sean, right? When you talked about precipitation reactions, acid-base reactions, redox reactions. It's when electrons are transferred from one species to another. When that species loses electrons, it's oxidized. When it gains electrons, it's reduced. And that always confuses some students, a lot of students. Reduced is a gain, okay? Oxidized is a loss, but that's just something you gotta commit to memory, all right? What's happening here? We have solid calcium combining with water to form calcium hydroxide, and then it releases hydrogen gas. So you have to look at the charge, the oxidation number, or the oxidation state for these species to see if it's oxidized or reduced. And we'll get into the rules. I don't know if Sean went into the rules of determining oxidation numbers or not, but we'll do it as either as a new thing or a refresher in just a minute. But calcium in its elemental form is going to be 0, right? But calcium in its new compound form of calcium hydroxide is +2, all right? So that means the charge went from neutral to +2. So it's positive. And if it's positive, that means it must have lost electrons, right? It lost negative charge to become positive. So that species was the oxidized species. Hydrogen, looking at the red arrow, hydrogen in that context is +1 in H2O. Hydrogen by itself in elemental form, like calcium, is 0. So it went from a positive, not to a negative, but it lost its positivity. So it must have gained an electron to bring it down to 0. Follow me? So it's gained electrons, it is reduced. Hopefully that clicks, because we're going to be doing this throughout the lecture today, okay? And if you don't understand this after we get into it in more depth, maybe revisit Chem 101 if you did it there, or talk to me about it, or hop on Discord and talk to your fellow colleagues. Okay, so again, we assign these different species what are called oxidation numbers so that we can kind of track what electrons are doing, okay? So again, zinc, solid zinc, let me get my annotation because I'm pointing to it, but you don't know that I'm pointing to it. Here, so solid zinc in its elemental form is 0. Aqueous zinc in its ionic form is +2. So what is that? Is that a gain in electrons, or is that a loss of electrons?
Loss?
Loss, yes, right? Because it gained a net charge, a net positive charge. So it must have lost electrons. Oops. All right. Then next we have hydrogen, which in its ionic form is +1, and then in its elemental form is 0. So it went from +1 to 0. It must have gained an electron, right, to bring it down from that positive to that neutral. And it doesn't just have, these are just examples where we've looked at 0 to a positive, but if you went from a +5 to a +2, you're gaining electrons, right? You're still positive, but you're less positive, okay? Likewise, if you go from a -5 to a -2, you've lost electrons because you're getting less and less negative. Okay, so here are the rules, right? These are hierarchical rules, meaning you apply the first rule, rule 1, first, when assigning charge, assigning oxidation numbers to these different species, all right? So if there's a conflict, you look at the rules above and work your way down. First rule is that elements in their elemental form have an oxidation number of 0, which we just worked on, right? So solid calcium is 0. Hydrogen gas is 0. The oxidation number of a monoatomic ion is the same as its charge, okay? So calcium in its ionic form would be what? What's its charge?
2+.
2+, right? It's in the second column of the periodic table. So that is also going to be its oxidation number. chlorine, 1 minus, right? It's also going to be a -1 oxidation number. Nonmetals tend to have negative oxidation numbers. However, that's not always the case. There are exceptions to most things. Almost all things in biology, many things in chemistry, very few things in physics, right? So we'll talk about that more a little bit in depth on the next slide, but that's rule 3. Rule 4, the sum of the oxidation numbers in a neutral compound is 0. Okay, so if there's no overall charge, that means the oxidation numbers must add up to 0, right? So if you have a compound that has a -2 charge in one species and a +2 charge in the other species of that compound, they neutralize and it's 0. And then 5, the sum of the oxidation numbers in a polyatomic ion is the charge on that ion, okay? So if we had a polyatomic ion that had a charge of -1, that could be because the oxidation numbers were -6 and +5, right? So the net is -1. Going back to rule 3, right? Nonmetals tend to be negative. Not always the case, okay? And not all nonmetals have the same oxidation number. Okay, so oxygen is usually -2 based on where it is in the periodic table. However, when it's in a peroxide ion form, it's going to be a -1. All right. Hydrogen, typically -1 when it is bound to a metal. However, it's +1 when it's bound to a nonmetal. Okay. So there are some exceptions, right? And you don't have to memorize all these things. You need to know those rules. It will help you navigate more quickly when you're doing these problems, right? But these things are in this slide deck for you to keep in mind. So you're not saying, oh, well, wait a minute. I thought hydrogen was +1. Why am I seeing it as a -1 here, right? You just gotta, and there'll be times where you have to figure out what the charge is based on what another species is that takes precedent in that hierarchical ruling system. Okay. Fluorine is always -1. However, other halogens can have -1, but they could have a positive oxidation number as well. Okay. So there will be some things that don't fit in the nice, neat box, and that's okay. Just be aware of it. Here's just basically those same rules in a different form with some examples, okay? I want to just go over these again just to kind of embed them into our psyche a little bit, okay? So again, we go through rules 1 through 5. 1 takes precedent over 2, 2 takes precedent over 3, and so on. First rule is that the oxidation state of an atom in its free elemental form is 0. Okay? So chlorine gas and just solid copper, 0. 2, the oxidation state of a monoatomic ion is equal to its charge. So calcium is a +2 because its charge is 2+. Chlorine is a -1 because its charge is 1-. The sum of the oxidation states of all atoms in a neutral molecule is 0. Okay? An ion is equal to the charge of the ion. So, for instance, NO3 right? That has a charge of -1. And then compounds such as metals are always going to have an oxidation state of +1 if they're in group 1. Metals are going to have an oxidation state of +2 if they're in group 2. So ions and metals tend to have, well, metals in the first two groups tend to have oxidation numbers that are the same as their charge. All right. And then the last one, in their compounds, nonmetals are assigned oxidation states according to the table at the right. Okay. So what that is saying is that based on these other rules that dictate what the oxidation number is for oxygen in that molecule, then we just have to fill in what the oxidation number is for the other atom or atoms in that compound to equal the overall charge. If that doesn't make sense, we are going to now practice it so that it will, okay? I recommend you review these rules a couple times just to let it sink in, okay? Here we go. What we need to do now is assign oxidation states to each atom in each element in these compounds, okay? So for instance, chlorine, what do you guys think chlorine is going to have as its oxidation state?
0.
0, exactly, because that is in its elemental form. 0, that's O. That is there. 0, okay, great. What about Na plus?
1 plus.
1 plus, exactly. What about potassium fluoride? Remember, fluorine is always -1. It's that halogen that is always -1. And there's no charge on this. So what must K be?
+1.
Exactly. +1. F is always -1. Okay. Carbon dioxide. Here we have 2 oxygens. Okay. What do we say the charge for oxygen was? It says -2. Okay. So 2 times -2 is -4. Oxygen is a -4. So if oxygen is a -4, what must carbon be?
+4.
Yeah, +4. Well, not positive money, although we could all use that. Carbon often is 4, also because of where it is in the periodic table, right? But it doesn't always have to be 4. It depends on what it is bound to and that rule that, takes precedent over it. Sulfur. Okay. Sulfur and oxygen. What do we have? So oxygen, let's just figure that out. -2. There are 4 of them, so that's a -8. What must sulfur be in this case to give us an overall charge of -2?
+6.
Exactly. Thank you. See, so pretty simple, right? Pretty simple. K2O2. What do we got for this? No charge. We know that oxygen is typically -2, right? What would we do for this? What do you guys think? Take a look at those rules. 4, okay? 4 for oxygen, I'm thinking. Let's, if you have your PowerPoint open, let's review the rules, right? So rule 5 is that the nonmetals are assigned their oxidation numbers based on what group they're in, right? So oxygen is in group 6, so it's a -2. And that's why we've been using it as a -2 for these ones above. But potassium is in rule 4, remember? It says that potassium, well, it doesn't say specifically potassium, but it says that group 1 always has an oxidation of +1, okay? Potassium is in group 1. So that means potassium has to be 2, +2, because there are 2 of them, right? So 1 times 2. And if that's the case, oxygen must also be a -1 because there are 2 oxygens, right? So -2. And that neutralizes it because as you see in F there, that has no overall charge, all right? So this is why knowing those rules is important, okay? Because some things, when assigning their oxidative numbers, take precedent over other things. So you've got to know what species you're acting, what species you're using, and where they fall in that overall grand scheme of things, being the rules. Generally, oxygen is going to be -2, mostly. Okay. All right, I'm going to have you guys work on this one. Let's see what you come up with. Okay, let's spend, what do we got? Let's spend 8, let's spend 10 minutes doing this. See what you get. All right, let's go ahead and just pick up a couple minutes early. I think that was probably enough time. And if not, we'll catch up those last couple together. Okay, so what'd you guys get for A? Zero. Exactly. Equals 0 because it's in its elemental form. What happens when it's in its ionic form? Now what? Exactly, +3. Okay. What do we get for carbon tetrachloride? There it is. Yep. So carbon is a positive 4. Chlorine is a -1, but there are 4 of them. So that leads to an overall charge of -4. Balances out, no charge on that molecule. Strontium bromide. Ooh. Which rule takes precedent? Not that it really matters, but what do you guys think? We know that bromine is -1 because of the group it's in. We know that strontium is +2 because of the group that it's in. So they're going to balance each other out anyway. But what if they didn't? Which one would you, which oxidation number would you assign first based on those rules? Close. It would actually be strontium because if we go back and look at those rules, oh, I'm going the wrong way. Rule number 4, group 2A metals always have an oxidation state of +2. Rule 5, in their compounds, nonmetals are assigned oxidation states according to the table at the right. That's this table here. So table at the right says that that bromine is a -1, okay? And there are 2 bromines, so that it'd be -2. But because strontium is that metal in group 2, it falls into rule 4. We assign that oxidation number first. Oops, why do I keep there? So, as I said, it doesn't matter really for this particular combination because they both cancel out anyway, right? But we would say strontium is first, equaling +2, and then bromine is going to be a -1. There are 2 of them, so -2. Okay, what about this? So we have 3 oxygens. Both of these fall into rule 5. So what we can do is we can look at the oxygens and say, well, there are 3 of them. 3 times -2 is -6. Sulfur, since there's no charge on this, therefore must be +6 to balance it off. Okay. And then finally, oxygen here is, again, -6. Nitrogen must be what? Exactly, +5, so that we end up with an overall charge of -1. All right. So now let's practice using oxidation states to find which species is oxidized and which is reduced. So what's the redox reaction? What is the oxidation reaction? Okay. Let's look at this here. So maybe I'll try to freehand it here. We'll see how legible I can write. Magnesium, solid magnesium, that's in its elemental form, right? So that's 0. Okay. 0. Here we have H2O. Remember that hydrogen is usually +1. Oxygen is usually -2. So let's go -2 for oxygen and +1 for hydrogen. Okay. Now we have magnesium hydroxide. So in this case, there are 2 hydroxide ions bound to magnesium. And hydroxide, if you guys remember from what we were doing earlier, is -1, right? So that has a -2 charge because there are 2. And then magnesium is in that second group, right? So it's going to be +2. So +2 for magnesium. And oxygen, we could look at this. We could look at this independently. We could say oxygen is a -2. Hydrogen is a +1. Hence the overall charge of a -1. And then hydrogen here is by itself. So it's it's by itself, but it's in its elemental form, hydrogen gas. So that's 0. Okay. So what is going on? Let's change the color here. What is going on with magnesium? It's going from a 0 to a +2. So what did it do? Did it gain electrons or did it lose electrons to get there? Gain or lose? Lose. Yes, because it went from no charge to a positive direction. So it must have lost electrons. So a loss is oxidation. All right. Let's do another color. Oxygen's staying the same, -2. But what's hydrogen doing? It's going from a +1 to 0. So that means it must have gained an electron, right? Because it went from no charge to a negative, or went from a positive charge to no charge. So that was reduced. Now we've defined which species have been oxidized, which have been reduced, and we've done it by looking at their oxidation numbers. Okay. Pretty handy little tool there. So I want you guys to do this one. How much time do we have? Okay. I want you guys to assign what is being oxidized, what is being reduced, and then we'll go over it and then we'll take a break. Okay. So work on that. Okay. Let's see what we came up with, shall we? What is tin in its elemental form going to have for its oxidation number? 0. Yes. Okay. Now, for this nitric acid, we have 3 oxygens. So that's -2 times 3. So a -6. We know that hydrogen is +1. So that means nitrogen must be a +5 because there's no charge on that acid. Okay. So we have 0 for tin, 1 for hydrogen, +5 for nitrogen, and -6 for oxygen. Notice the coefficients don't play into this because we're just looking at a particular species level, not how many of them are in the solution. Okay, so even though there's a 4 here, we don't take that into consideration. Now over here, oxygen's a -2, tin +2. That neutralizes it out, no charge, so we're good there. So something's happened with the tin already. With water here, oxygen is 2. Come on, back to me. Is a -2. Hydrogen is +1. There are 2 hydrogens in that molecule, so it's going to be 2 times a +1 to balance it out. So that doesn't change. I can write it like this.
I'm not sure it matters in figuring out the oxidation and reduction, but isn't the tin on the products +4 and the oxygen -4?
Oh, yep, you're right. Thank you. How do I erase? Absolutely. Thanks, Hannah. Yes. It's -4 because there are 2 oxygens there, right? Absolutely. So then tin would be +4. Good call. Doesn't matter, but it is correct, and being correct does usually matter. Okay, and so what's left? Now we have nitrogen, 2 nitrogens, so that's a -4. And it's not charged, so I'm sorry, 2 oxygens. I don't know if I think I said nitrogens. 2 oxygens, -4, no charge. So this nitrogen must be a +4. And so now we see what's changed here, right? 2 things have changed. I don't want to let me write. 2 things have changed. The tin has changed from 0 to not +2, but +4. So that means it's lost electrons to gain that positive charge. So that is, oh gosh, man, my drawing tool keeps disappearing on me. That's oxidized. Okay. And then the nitrogen has gone from +4 or +5 to +4. It must have gained an electron to bring that charge down. Still positive, but less positive. So gain an electron is overall going to be reduced. Okay. Oh, bother this drawing tool. There we go. D. That's it, guys. That's how we do this. All right. Why is all of this important? Well, you'll see after the break. Let's take a 10-minute break and come back at 4, 2, I take that long of a break. Let's come back at 2:15. Okay. All righty. Let's get back to it. Let's clear this stuff off here. Here's another problem where you can determine whether or not the reactions are redox. Hint, I think only one of them is a redox. In the interest of time, I'm not going to go over this. But if you want to, for more practice, look at these, assign their oxidation numbers, and then see if anything is gaining or losing electrons. If they're not, then it's not going to be a redox reaction. But if they are, then they are. And then maybe see what you come up with, and shoot me a message. Let me know if you find an answer. Okay. What I want to focus on now is balancing half reactions. Okay, this is a process. We're going to do this, and then hopefully we'll have time to. What time is it now? Yeah, hopefully we'll have time to practice one or two. And then, there'll be an ICA where you can do some more of this, okay? So strap in, open your minds, and we'll begin, okay? Half reactions are where we break up the oxidation and reduction into two separate reactions, hence half reactions, okay? So we take what species are being reduced and which species are being oxidized, and we break them apart into their own reactions. And then we balance them. We balance them using water and electrons and all that stuff. And then we combine them back together. We see what cancels out, and we get our kind of, our net reaction like we were doing earlier. Okay. In lab. So this is how we do it. Okay. We assign our oxidation numbers to determine what's oxidized and what's reduced, as we've just been doing. And then we write out those as half reactions. Okay. Once we have our two half reactions, and we say half reactions because we're going to combine them back into one reaction. Once we have our half reactions, we balance the elements besides the hydrogens and oxygens with coefficients, right? So just like you're balancing a regular reaction. And then we balance the oxygens by adding water to one side. Okay. So for instance, if we had magnesium in its elemental form and it turns into magnesium hydroxide, now there's oxygen there, we would add H2O to get oxygen on the other side. We balance the hydrogens by putting hydronium ions on one side. So we treat it like an acid. And then we need to find the least common integer between those two half reactions to balance everything out. Okay, so we multiply the half reactions by some number that will then lower the number of electrons and stuff like that and crunch it down a little bit. All right. Maybe that makes sense. Maybe it doesn't make sense yet, but I want to give you the steps that we take before we just jump into it so that you can have an idea of what we're going to do here. All right. If it is a reaction that occurs in a basic solution, doesn't matter. We're going to balance it as if it occurred in an acid. Okay. So we're going to have those hydronium ions that we'll use to balance the hydrogens. Okay. And what's going to happen is the hydroxide ions are going to neutralize. Okay. And so that's going to form water. Once you have water on both sides, we can subtract that water. If it's different numbers of water, we just reduce the number of water in the equation. Okay. let's try it, okay? We have permanganate and we have oxalate, and that's going to form just manganese ions and carbon dioxide. So the first thing we have to do is figure out what's being oxidized, what's being reduced, and then write those out as reactions, okay? So to do that, we can say that, let me get my little annotation going here. We have 4 oxygen. So that is -8. And because there's this negative charge here, that means that the manganese must be a +7, right? To get that overall charge of -1. Here, manganese is by itself, 2+. So we just say that that's going to be the oxidation number, +2. Here, carbon is +3. Why? Because we have, again, 4 oxygen. So that's, why is this negative? I don't know why my annotation thing doesn't want to work, but -8. But here, it's a charge of 2-. So that means this carbon must be a +3 to make overall charge of +6, because it's C2, okay? However, over here, right, we have O2, which is -4. Carbon must therefore, since there's no charge, must be 4. So from all that, we can see that manganese is going from a +7 to a +2. So it has gained electrons and therefore is reduced. Carbon goes from +3 to +4. So it's lost electrons, it's oxidized. Okay. If you guys are struggling to get this, what we've been doing, what we're doing now, it's important that you figure it out so that we can continue to progress. So if you want to see chapter 7 in your textbook as a refresher on assigning charge, I recommend that you do that. Okay. If you're feeling pretty good, then we'll just keep going. All right. So we know what's reduced. We know what's oxidized. The next step is to write out these half reactions. Okay. So we're saying here that this is going to manganese and this is going to carbon dioxide. Okay. So we can just, it doesn't matter which one we start with really, but if we want to have the oxalate going to carbon dioxide, we can write that out as a half reaction. It's not balanced though, right? Because we have 2 carbons. Come on. We have 2 carbons here, but just 1 carbon here, right? So we add our 2 here. Now that's balanced, but, oh, and the oxygens are balanced, so that's good. All right. So then we go on to the next step, which is to now balance the charge, right? You see here that the charge is going to be for oxalate 2 negative. There is no charge on carbon dioxide, so we add 2 electrons to this side of the half reaction. Now each side has a -2 overall. Okay, overall on each side, -2. So now it's neutral. Perfect. Going good so far. Let's do the next half reaction. So we have permanganate going to manganese. Well, what's the difference? Looks like manganese is okay, but there's no oxygen on that side. So we add the water right here. We add this water. All right. That will give us 4 oxygens here to balance out the 4 oxygens on this permanganate. And then manganese is just 1. So that's good. But now we got to keep going because now we've added hydrogen to the right side. Yeah. So let's add the hydrogen. Let's add those hydronium ions, the hydrogens to the left side. Okay. So now we've added these 8 hydrogens right here because there are 8 hydrogens on this side. So overall, we end up with 8 hydrogens, 1 manganese, and 4 oxygens. And it's balanced on either side by just adding waters and hydrogens. But what isn't, now let's look at the charge, okay? Let's look at the charge. What is the charge? Well, we have 8 hydrogens, which is +1. Okay, so 1 times 8 is +8. And then this is overall -1. So that means cumulatively on the left side, we have a +7. All right. Over here, we have +2. All right. So to balance that, we add 5 electrons to the left, right? Because 5 electrons are going to bring that +7 down to a +2. So that's why it's right here. Okay. 5 electrons, 8 hydronium ions, 4 waters on the other side. That's what we've added to now balance this equation. Hopefully you're still with me. So now what? Both of them are balanced. Now we put them together. We have our oxalate going to carbon dioxide and 2 electrons. And then we have our 5 electrons and 8 hydronium ions and permanganate going into manganese and 4 waters. Now we have different numbers of electrons though. We have on this side 2 electrons, on this side 5 electrons. And so the way we get around, the way we balance that is that we find the least common integer for these 2 things, which is 10, right? 5 times 2. So to balance the electrons, we multiply everything in this half reaction by 5. And everything in this half reaction by 2. Okay. And so that's going to give us 2 times 5 electrons, 10. 2 electrons times 5, 10. So each half reaction now has the same number of electrons so that when we write our overall net equation, we get rid of the electrons. We don't want them in there. Okay. So when we do that, when we multiply everything up top by 5, in that first half reaction, we get 5 oxalate goes to 10 carbon dioxide plus 10 electrons. 10 electrons plus 16 hydronium ions and 2 permanganate yield 2 manganese and 8 H2O. Okay. And so now we stitch these together by putting all the things on the left side of the arrow on the left side. So this is all going to go here. And this is all going to go here. Okay, and now we have this one big, long, not half reaction, but full reaction. And we can start getting rid of things, right? We can get rid of the 10 electrons, for instance. We can start reducing other things, right? We have all these hydrogens. We have H2O. Let's see what we can do. Now we have it whittled down. We remove these electrons, okay? So the electrons are out of the equation. Now we have 16 hydronium ions, 2 permanganate, 5 oxalate, so on, so forth. Okay, we're crunching it down. Oh, and that's it. Any questions on that? You guys all got that? Or you just don't want to ask questions? Okay, let's do one on the board together, shall we? Here we go. Let's see what we can come up with this. Do you guys want to, can let you guys try one if you want. Go into breakout rooms and try one, or do you want me to do one on the board? Is anybody there? Did we come back from break?
I think it would, at least for me, be helpful to do it a little slower, just because writing it down, I was really having a hard time keeping up with this stuff.
All right. Well, let's do one now on the board together. Let me write this out. I'm going to just leave out the aqueous in brackets there just to save room. Okay. All right. Well, I want to pin. There we go. Okay. So this is our reaction. First thing we need to do is see what's oxidized and which is reduced. Okay. So wait, did we just, no, we did, well, we did one very similar to this, right? So we know that this is a -8 and this must be a +7, right? And this is +3. This is +2. And this is -14. So this is a +7 because there are 2 there. Oh no, but we don't want it to, we want a -2 charge, so +5. So if we look at this, manganese must have gained electrons to go from a +7 to a +2. So that's oxidized. Chromium went from +3 to +5, so it must have lost electrons. So it is reduced. All right. So now we write our half reactions. We say that.
I had one question. Would the chromium be 6 or 5 for that? Just because I thought For
It'd
it
be
to be,
6. You're right. It'd be 6. Sorry.
oh, no worries. Thanks.
6 times 2 is 12. I can do the more complicated math. Apparently, I can't do the simple math. Yes, thank you for catching that. 6. Either way, it still changes it for the positive. So we write out our half reactions now. We're saying that manganese or permanganate goes to Mn2 plus. Let's start with that one. Okay. What do we need to do? We need to add something to get oxygen, right? We need to add H2O. And we need to add 4 of them. Sorry, I'm in the shadows here. Okay. So that's good. Manganese is okay. But now this has a positive 2 charge, right? So what does that mean? That means we need to add some electrons somewhere. Oh, this is negative. Okay. So how do we get that going?
Would we add an electron on the right?
Yeah, so if we added 1 electron, that gets this down to positive 1.
Oh, would we add 3 electrons to make them even then?
Yeah. Before we do that, we got it. Let's add the hydrogen, because remember we added water to get the oxygen, but now we have hydrogen on this side, and we have 4 times H2. So let's add 8 hydrogens here. Okay. Now we have 8 hydrogens, 1 manganese, 1 manganese, 4 oxygens, 4 oxygens. Okay. Now our charge cumulatively is what? Positive 7, positive 2. So now, what do you think the electrons would be? We want to get
7 on the left and 2 on the right, or is to even it out?
What if we just add to one side? So if this is 7 here, if we added 5 electrons, that would bring this down to a positive 2.
Oh, so each side doesn't have to equal 0, just the whole.
Yes.
Okay.
Overall, exactly. Okay. So let's add 5 electrons. And now this charge is positive 2. This charge goes from positive 7 down to positive 2. Okay. So that's, I should make that blue. Okay, and let's shorten this arrow and just say plus 5 electrons. I think that's good now. Everything is balanced in that half reaction, right? So then let's go back to the other one. I'll make that red. Say chromium 3 plus goes to oxalates 2 minus. Okay. Well, we got to get some water here, right?
would we start by balancing the chromium, or is that not?
We could. In this case, you know, we can balance the chromium. Yeah, you're probably, in the way that I wrote it out, you know, you want to balance everything before you start adding water. So good call. So we added 2 there. Now it's balanced. Then we add the water. We need what, 7? 7 oxygens. 7 oxygens. What else? We need hydrogens, right? We've introduced, how many? We've introduced 14 hydrogens on this side. So let's do 14 hydrogens on this side. Okay, 14 hydrogens, 7 oxygen, 2 chromium. Now we got to think about the overall charge. So here, it's +3. And over here, it looks like it's +12 to me, right? Because H1, H positive 1, but there are 14 of them. -2, 12.
So would we add 6 electrons to the product side?
So if we add 6 electrons here, that would bring us down to, all right, because there's 2 chromium.
Yeah, because I got my net charge on the left to be 6 and then 12 on the right.
Okay. Yep. Because of the 2 chromium. Right. So rewrite this over here. +6 electrons. So I think everything's balanced now. Now we just got to stitch them together. We got to balance the electrons. So here we have 5 electrons. Here we have 6 electrons. We want to get those electrons the same. So just like we did in that previous problem, it was 5 and 2, I think. 5 and 6 is 30. That's the least common integer for them. So if we multiply all of this by 6 and all of this by 5, we should be good to go, right? So let's try that. Let's see what happens when we multiply that out. That would be all of this times 6 and all of this times 5. Okay. So let me switch to yet another color. And we get, let me do the top one first. Electrons. Actually, write it up. I'm going to erase this and write it above because I'm running out of board space. So 6 times all of this stuff. So this plus 6 and 4 plus 30 electrons gives us 6 manganese plus 24 H2O. Okay. You follow me so far?
Yeah.
Okay. Now, can we simplify that at all? We can. We can simplify the water. 24 over here, 48 over here. So if we just canceled out those 24, right? If we divide each of them by 24, we get rid of them on that side, and we get 24 here.
I'm just a bit confused because I had 48 hydrogen ions, not 48 waters on the product side.
Oh, shoot. You're right.
Okay. No,
That was correct. Thank you. So wait, what did I have? I had 24 H2O. I wrote that wrong. Yeah, that's hydrogen. My bad.
Oh, okay.
48 hydrogen. Sorry. Yeah, it's right here. Okay. Good catch. Thank you. All right. So then that means we can't cancel anything further. Let's write this other half reaction out. So that is 35 H2O, 10 chromium, and that gives us 5 chromate plus that's 5 times 14, 70. I don't know if that's right. Plus 30 electrons. Okay. So now what? Did I do that right?
You could cancel the electrons in the hydrogen ions and some of the waters.
Okay. So let's do that. 30 electrons, those cancel. We have 70 hydronium ions and 48. So if we cancel out the 48, that would leave 22. And 35 waters and 24 waters. We cancel out all 24. And that'd be what, 11? Okay. Looking good so far, I think. And let's write it out. So we write out everything on this side. So we have 6 permanganate plus, that's everything there, plus 35 H2O plus 10 chromium.
It's 11 now.
Oh, 11, thank you.
Or on the H2O.
Yep. Oh, thank you. Thank you. This is why I need you guys. That looks right. Okay. And then we write everything on this side. That's going to be 6 manganese plus, I'm going to need more room. Let's write it in blue. Six Mn plus 5 Cr2O7 2 minus plus 22 H plus. Yeah? And let's see if everything balances out, shall we? We have 6 manganese, 6 manganese. We have 24 oxygens plus 11 oxygens, 35. So 35 oxygens. 5 times 7, 35. Okay. We have 10 chromium, 5 times 2, 10. We have 11 times 2, hydrogen is 22. Bam, 22. We did it together. Good job. And we're out of time. So I think there's one more problem. That I wanted to go over, this one. But since we are now out of time, we won't do that. Any questions on that? Okay. That second problem that we're not going to go over is in the OpenStax textbook. So if you want to try it out and then check yourself, go to OpenStax, okay? And look it up. The ICA for next week is going to be just 2 problems like this. It'll be asynchronous, so just do it whenever you want. Review this recording. Look at how they do it in the book. Go from there. Use Discord to get together if you want to work in teams. And it should be no problem. Watch the video. Watch the Jennifer Doudna talk. And we'll return back to synchronous learning after next week. You're free to go. If you have any last minute questions though, I'm happy to stay on for a few minutes.
Thank you. See you next week.
All righty.
Or the week after.